the kingdom of giants. In the quiet reaches of our solar system, more than 400 million miles from Earth, a colossal world reigns. A planet so vast that it could hold more than 1,000 Earths within its swirling clouds. A gas giant whose presence has shaped the very architecture of our cosmic neighborhood. This is Jupiter, the king of planets. But tonight, we turn our gaze away from the planet itself and toward the shadows that orbit it, toward the worlds that dance in its eternal gravity. 4 of them stand apart, immense and ancient. They are Io, Europa, Ganymede, and Callisto, the Galilean moons. Each one a world in its own right. Each one holding secrets that may redefine everything we think we know about life, geology, and the very nature of planets themselves. When the Italian astronomer Galileo Galilei first pointed his crude telescope toward Jupiter in the winter of 1610, what he saw changed humanity's place in the universe forever. 4 small points of light moved from night to night around Jupiter, proving something radical for the time. Not everything revolved around the Earth. Those faint lights, barely visible through early glass, became the first proof that the cosmos was far grander and far stranger than we had ever imagined. 4 centuries later, those same points of light now beckon us once again. But this time we see them not as distant specks. We see continents of fire, oceans beneath ice, and mountains higher than Everest. We see the fingerprints of creation, preserved in frozen crusts and molten cores. Jupiter's moons are not lifeless rocks. They are living laboratories, places where gravity, magnetism, and chemistry combine to create breathtaking extremes. Io burns with volcanoes that never sleep, spewing molten sulfur hundreds of kilometers into the sky. Europa hides a vast ocean beneath its gleaming ice shell, an ocean that may cradle life even now. Ganymede, the largest moon in the solar system, boasts its own magnetic field, hinting at a metallic heart. And Callisto, dark, ancient, and scarred, may be the most well-preserved relic of the solar system's youth. These worlds are not distant curiosities. They are chapters in our own cosmic story, fragments of the same materials that built Earth, shaped Mars, and stirred the clouds of Jupiter itself. We are entering an age where robotic eyes and human curiosity pierce those distant veils. NASA's upcoming Europa Clipper and the European Space Agency's JUICE mission will soon sweep past these moons, sending back whispers from worlds we've only dreamed of. They will fly through plumes of vapor that shoot into space from Europa's hidden ocean. They will map the tortured plains of Io and measure the radiation belts that rage through Jupiter's magnetic empire. And with each passing orbit, they will draw us closer to understanding whether life in some form might thrive beyond our tiny blue. In this journey, we will travel beyond Jupiter's turbulent storms, past the great red spot, through the vast fields of radiation and the planet's shimmering auroras, to the moons that hide in its shadow, the places where fire, ice, and time have sculpted alien worlds of incomparable beauty. We will walk across Io's rivers of lava, dive beneath Europa's frozen crust, feel the magnetic hum of Ganymede's iron heart, and gaze upon the silent scars of Callisto, a world older than any earthly mountain. This is not merely a story about Jupiter. It is a story about creation itself, about how planets are born, how they evolve, and how, even in the coldest corners of space, the spark of life might still. So settle in, let the darkness surround you, We are going to a place where sunlight fades, where time moves slowly, and where the boundaries between science and mystery begin to blur. Welcome to Beyond Jupiter, the hidden secrets of its mysterious moons. Chapter 1. Galileo's Legacy Beyond the Gas Giant. In January of 1610, a man in Italy lifted a crude telescope toward the night sky. His name was Galileo Galilei. The instrument he held was simple, a tube of glass and metal, no more advanced than a pair of opera lenses today. Yet through that fragile tool, humanity's vision expanded farther than it had ever reached before. When Galileo focused his lens on Jupiter, he saw not one point of light, but 5. One was Jupiter itself, a bright, steady beacon. But 4 smaller stars appeared to shift their positions night after night. They moved in unison, orbiting the great planet. Galileo realized something profound. These were not stars but moons, celestial bodies circling a planet other than Earth. This single observation shattered centuries of belief that all heavenly bodies revolved around our world. For the first time, humanity understood that Earth was not the center of creation, but one planet among many in a vast, dynamic cosmos. Those moons would later be named Io, Europa, Ganymede, and Callisto, the Galilean moons. They were the first discovered beyond our own, and they remain the most studied and enigmatic satellites in the solar system. Each one is unique, complex, and full of contradictions. And together they tell a story not just about Jupiter, but about the formation of planets, the potential for alien life, and the endless processes that shape the universe. Centuries have passed since Galileo's discovery, yet the same sense of wonder he felt still drives our exploration today. The telescopes of his era have evolved into space observatories, orbiters, and robotic explorers capable of crossing 500 million miles to reach Jupiter's domain. But the question remains, why do we keep returning to these moons? Why do they hold such fascination for astronomers, planetary scientists, and dreamers alike? The answer begins with Jupiter itself. Jupiter is more than a planet. It is a miniature solar system, a gravitational giant so massive that its presence dominates everything around it. Its magnetic field stretches millions of kilometers into space. Its gravity sculpts the orbits of its moons, tugs at the asteroid belt, and even helps shape the early evolution of our solar system. Without Jupiter, Earth might never have formed as it did. The gas giant acted as both guardian and destroyer, shielding the inner planets from deadly impacts while hurling icy bodies inward that brought water and organic materials. The Galilean moons orbit within this immense gravitational and magnetic domain, constantly molded by it. They are pulled, stretched, and heated by Jupiter's tidal forces. Their surfaces crack and erupt. Their interiors churn with hidden energy. In many ways, Jupiter's moons are not passive companions. They are active participants in a cosmic symphony of gravity and motion. To understand Jupiter's moons is to understand the history of planetary formation itself. Around 4.5 billion years ago, the solar system was a swirling disk of gas and dust orbiting the newborn sun. In the outer regions, where temperatures were cold enough for ice to solidify, Jupiter began to form. As it grew, it gathered a miniature disk of its own, a subnebula. Within that swirling material, smaller bodies coalesced, just as planets had formed around the sun. Out of that disk, the Galilean moons were born. Asia formed closest to Jupiter, composed mostly of silicate rock. Europa came next, with a mix of rock and ice. Ganymede grew larger, containing both silicate materials and vast amounts of ice, becoming the biggest moon in the solar system. Callisto, farthest away, remained the most untouched, a relic from the ancient past, its surface a record of billions of years of impacts. Each moon carries the imprint of its origin. Io is dominated by heat and motion. Europa hides water beneath its frozen skin. Ganymede is a world with its own internal magnetic field, something no other moon can claim. Callisto is quiet, scarred, and ancient. Together, they present four different outcomes of the same formation process, each shaped by its distance from Jupiter and by the gravitational forces that bind them all. When Galileo saw those tiny points of light, he could not have imagined what they truly were, worlds with mountains, oceans, and volcanoes. He could not have known that one day spacecraft would fly past them, capturing details finer than any earthly mountain range. In 1979, more than 3.5 centuries after Galileo's discovery, the Voyager spacecraft sent back the first close-up images of these moons. The world was stunned. It appeared as a sphere of sulfur and fire, the most volcanically active body ever seen. Europa gleamed like cracked glass, its icy surface fractured into vast plates that hinted at something liquid below. Ganymede looked like a planet unto itself, with ridges, plains, and polar ice caps. Callisto was dark, ancient, and battered, a fossil world untouched by geological renewal. Each of these discoveries deepened the mystery. How could four moons orbiting the same planet be so completely different? The answer lies in a delicate gravitational dance known as orbital resonance. Io, Europa, and Ganymede are locked in a rhythm, a 1 to 2 to 4 resonance, meaning that for every orbit Ganymede completes, Europa circles Jupiter twice and Io completes 4 orbits. This gravitational pattern constantly stretches and compresses the moon's interiors, generating enormous amounts of heat through tidal friction. It is this relentless pulling that keeps Io's volcanoes alive and may maintain the liquid ocean beneath Europa's ice. That same gravitational relationship also makes the Jovian system one of the most dynamic and complex environments in the solar system. Jupiter's immense magnetic field interacts with the charged particles emitted from Io's volcanoes, creating intense radiation belts and dazzling auroras that stretch across the planet's poles. Each moon leaves its mark on Jupiter's environment, influencing the planet just as they are influenced in return. The Galilean moons are not only scientific marvels, they are philosophical ones. They remind us that even within one planetary system, nature produces astonishing diversity. Within Jupiter's orbit we see extremes, heat, ice, magnetism, silence. And beyond those extremes lies the possibility that one of these worlds could harbor life. As the 21st century unfolds, new missions are preparing to revisit Galileo's discoveries with modern tools. NASA's Europa Clipper mission and the European Space Agency's JUICE spacecraft are now on trajectories that will take them deep into the Jovian system. They will scan the moon's surfaces with radar, sniff their atmospheres, and analyze their magnetic environments. Their goal is to uncover the hidden layers of these worlds, to determine whether water flows beneath Europa's crust, whether Ganymede's core still churns with molten metal, and whether Callisto hides traces of a long-forgotten ocean. The legacy of Galileo lives on in these missions. His simple observation, 4 moving lights around Jupiter, became the foundation for modern astronomy. What began as curiosity through a telescope has become a scientific quest spanning centuries. The same 4 moons that redefined humanity's place in the universe now challenge our understanding of life, energy, and planetary evolution. Jupiter's domain is a system within a system, a place where creation and destruction coexist. The planet's gravity sculpts its moons, its radiation scours them, its magnetism binds them in invisible threads of power. And yet, amid all that violence and motion, these worlds remain stable, locked in rhythm, orbiting endlessly in a gravitational ballet that has lasted billions of years. As we look ahead, we stand on the threshold of rediscovery. The data gathered in the coming decades will not only reveal more about these moons, but also about how planets like Earth came to be. The lessons of Jupiter's moons reach far beyond the gas giant itself. They touch on questions that define us. How did life begin? How does it survive? And could it exist elsewhere? Galileo's telescope may have been small, but the legacy it began is infinite. From the cold mountain tops of Earth to the robotic explorers sailing toward Jupiter, the same impulse drives us to see what lies beyond, to understand what we do not yet comprehend, and to find our place in the vastness of space. Jupiter's moons, once mere points of light, have become mirrors reflecting the story of our own beginnings. They are testaments to curiosity, endurance, and the boundless reach of human wonder. The legacy of Galileo endures not in stone monuments or written pages, but in the shining faces of 4 distant worlds, circling a planet of storms, whispering their ancient secrets across the void. That is Galileo's true gift to us, not the telescope, not the data, but the realization that every world, no matter how small or distant, has a story to tell. And as we journey deeper into Jupiter's realm, we are finally ready to listen. Chapter 2. Io, the Volcanic Inferno. Among all of Jupiter's moons, one burns brighter and wilder than the rest, Io, the closest of the Galilean moons to Jupiter. It is a world where fire replaces ice, and where the surface itself never sleeps. To look upon Io is to witness a planet in constant upheaval, a place of sulfur, lava, and relentless change. Io is unlike any other moon in the solar system. Its entire surface is shaped by volcanoes. Not just a few, but hundreds of them, towering calderas, rivers of molten rock, and fountains that hurl lava and gas hundreds of kilometers into the black sky. It is the most volcanically active body known to science. Every inch of its landscape tells a story of heat and fury. Mountains taller than Everest rise above plains of ash and frozen sulfur. Entire regions are repaved with fresh lava flows every few years. Where other moons are ancient and scarred by impacts, Io's face is constantly renewed by eruption after eruption. The reason for Io's restless nature lies in its position within Jupiter's gravity well. The planet's immense pull stretches and compresses Io's interior on every orbit. The moon is caught in a gravitational tug-of-war with Jupiter and its neighboring moons, Europa and Ganymede. This constant flexing generates enormous internal friction, heating Io's core to temperatures high enough to melt rock. What would be a frozen world elsewhere becomes, Under these forces, a planet of fire. From a distance, Io glows with an eerie palette. Yellows, oranges, reds, and whites blend across its surface like the pigments of a dying star. The colors come from sulfur and its various compounds, deposited by erupting plumes and frozen by the bitter cold of space. The result is a landscape both violent and beautiful, like a painting in motion. When Voyager 1 flew past Io in 1979, scientists expected to see a cratered moon. Instead, they found something extraordinary: vast plumes rising over 300 kilometers into space, captured by the spacecraft's cameras as towering arcs of dust and gas. These eruptions were unlike anything seen before. It was proof that Io was alive, geologically speaking, a moon constantly reshaping itself, driven by forces no one had anticipated. Later missions, such as Galileo in the 1990s and New Horizons in the 2000s, revealed even more detail. They showed that Io's surface was not only active, but diverse. Some volcanoes erupt with slow-moving lava flows, while others explode with sudden violence, releasing fountains of molten material at thousands of degrees. Some of these eruptions are so powerful that they can be seen from Earth with large telescopes, brief flares of reflected sunlight glinting off molten lakes. At the heart of this inferno are volcanoes like Loki Patera, a vast lava lake more than 200 kilometers across, larger than some nations on Earth. The lava crust periodically collapses and renews itself in massive overturning events, making Loki one of the most powerful volcanic features anywhere in the solar system. Elsewhere, plumes from volcanoes such as Peel spew sulfur dioxide high into the thin atmosphere, painting the surface in rings of red and black. Io's atmosphere is tenuous, a whisper of sulfur dioxide gas that freezes and evaporates as the moon moves in and out of Jupiter's shadow. When sunlight fades, the atmosphere collapses onto the surface as frost. When Io emerges back into sunlight, the frost vaporizes once again. It is a world that literally breathes in rhythm with Jupiter's orbit. The interaction between Io and Jupiter is one of the most dramatic relationships in the solar system. The moon's volcanoes eject vast quantities of charged particles into space. These particles form a plasma torus, a donut-shaped ring of ionized gas that encircles Jupiter along Io's orbit. As Io moves through this plasma, it generates powerful electrical currents that travel along magnetic field lines to Jupiter's poles, creating brilliant auroras in the planet's atmosphere. The connection between the two worlds is not just gravitational, but electromagnetic, a continuous circuit of energy flowing through the void. Io's surface may appear alien, but in many ways it helps scientists understand the processes that shape planets everywhere. The tidal heating that drives its volcanism offers clues to how internal energy sources can affect planetary evolution. On early Earth, similar heating and volcanic activity may have played a crucial role in forming the continents, the atmosphere, and even the conditions that allowed life to begin. Io, in this sense, is a glimpse into our planet's own fiery infancy. Yet for all its power, Io is also a world of balance. Every eruption releases energy that is built up within. Every plume that rises eventually settles as frozen sulfur snow. The landscape is constantly changing, but the moon itself remains in dynamic equilibrium, its orbit and shape maintained by the same gravitational forces that ignite its fury. Io challenges our understanding of what a moon should be. It is neither quiet nor dead. It behaves more like a miniature planet, active, unpredictable, alive with energy. And despite the harshness of its surface, Io's internal mechanisms provide insights that reach far beyond its volcanic plains. Scientists have long wondered how Io sustains such extreme volcanism over billions of years. Tidal heating explains much, but there may be other contributing factors. Some models suggest that Io's interior may contain layers of partially molten rock that circulate like a slow, fiery ocean beneath its crust. Others propose that electrical currents induced by Jupiter's magnetic field generate additional heat deep inside the moon. Whatever the exact mechanism, Io demonstrates that even small worlds can harbor immense internal power if the conditions are right. In a broader sense, Io also serves as a natural laboratory for understanding how energy flows through planetary systems. Its interaction with Jupiter's magnetic field creates radiation belts that can damage spacecraft and challenge exploration efforts. Studying Io helps engineers and scientists design future missions capable of surviving the intense radiation environment near the gas giant. But beyond the science lies something deeper, a realization of nature's extremes. Io is both terrifying and mesmerizing. It shows us that beauty in the universe does not always come in gentle forms. Sometimes it emerges from chaos, from heat, from destruction and renewal. The same forces that tear Io's surface apart also create landscapes of astonishing color and form. From the distant eyes of our telescopes, Io flickers like a tiny ember against the vastness of space. But up close, it is a roaring world, alive with motion and change. Every orbit, every eruption, every plume of gas adds another chapter to a story that began billions of years ago, a story of gravity, heat, and unending transformation. Io is proof that the solar system is not static. Even now, as we orbit our quiet Earth, volcanoes rage hundreds of millions of miles away, powered not by sunlight or atmosphere, but by the invisible pull of a giant planet. It reminds us that the forces that shape worlds are universal: gravity, motion, and time, working together in endless cycles. As we leave Io's glowing horizon behind and turn our gaze outward, another world awaits, colder, quieter, but perhaps far more profound. Beneath its icy crust may lie an ocean vast enough to hold more water than all of Earth's seas combined. A place where darkness hides possibility. Europa, the moon of ice and perhaps of life. Chapter 3. Europa, ocean beneath the ice. Europa, a world that gleams like a frozen pearl in the faint sunlight, orbiting its colossal parent, Jupiter, once every 3.5 days. At first glance it seems serene, smooth, pale, and silent. But beneath that icy crust lies one of the greatest enigmas in the solar system. Europa is more than just a moon. It is a world with an ocean so vast, so deep, that it may contain more water than all of Earth's oceans combined. And hidden within that ocean may be the most profound discovery humanity has ever dreamed of: life beyond Earth. For centuries, Europa was little more than a point of light through a telescope. Galileo named it after one of Jupiter's mythic lovers, never imagining that beneath its bright surface could be an entire alien ocean. For hundreds of years, its mysteries remained sealed under an icy crust tens of kilometers thick. But the hints were always there, subtle clues that the smooth, cracked plains of Europa were unlike anything else in the solar system. When the Voyager spacecraft flew past in 1979, scientists expected to see a cratered, dead moon, pocked and ancient like our own. What they found was the opposite. Europa's surface was almost entirely unmarked by craters. It was smooth, bright, and crisscrossed by dark streaks and fractures that seemed to stretch for thousands of kilometers. These lines looked like veins, scars on a living body. Something beneath was reshaping the surface, renewing it. The moon was active. Further flybys by Galileo's namesake spacecraft in the 1990s revealed even more astonishing details. Vast ridges and bands twisted across Europa's surface, some raised as high as mountain ranges, others sunk deep into the ice. Patches of disrupted terrain, called chaos regions, appeared where the surface seemed broken and refrozen, as if the crust had melted and refrozen multiple times. These were not random formations. They hinted at powerful processes beneath, perhaps the flexing and heating of an immense liquid ocean. The mechanism driving all of this lies in Jupiter's relentless gravity. Europa is locked in a gravitational dance with its neighboring moons Io and Ganymede. Their orbits tug rhythmically on Europa, stretching and squeezing it as it circles Jupiter. This tidal flexing generates internal heat, not enough to melt the whole moon, but enough to keep vast reservoirs of water beneath the surface from freezing solid. The result is a global ocean trapped under a thick, icy crust. We have long known that where there is liquid water, energy, and chemistry, there is potential for life. On Earth, entire ecosystems thrive in darkness at the bottom of our oceans, around hydrothermal vents that spew hot, mineral-rich water into the abyss. Microbes feed on the chemical energy from those vents, forming the foundation of ecosystems completely independent of sunlight. If similar vents exist on Europa's seafloor, they could provide the same conditions for life, simple, microscopic, perhaps even multicellular, evolving in an alien ocean, untouched by light for billions of years. The idea seems like science fiction, but evidence continues to mount. The Hubble Space Telescope has observed plumes of water vapor erupting from Europa's surface, immense, geysers shooting hundreds of kilometers into space. These plumes suggest that the ocean below occasionally breaks through the crust, releasing material into space. If these plumes truly originate from the subsurface ocean, then future spacecraft could sample them directly, flying through the vapor and analyzing its chemistry without ever having to drill through the ice. Europa's surface itself also tells a chemical story. Observations show traces of salts and complex molecules, possibly carried upward from the ocean below. These substances, when exposed to Jupiter's intense radiation, form reddish-brown stains across the ice. It's as if the moon's hidden sea is leaking tiny hints of its secrets to the surface, chemical fingerprints from an unseen ocean world. Consider the scale of this hidden realm. Europa's ocean may be 60 to 150 kilometers deep. Beneath that, there could be a rocky seafloor, heated by the same tidal flexing that stirs the ice above. The energy released could drive hydrothermal activity, vents, fissures, and chemical reactions similar to those on early Earth. And if that's true, then Europa may not just resemble Earth, It may be a living mirror of our own planet's ancient past, when life first began in the darkness of primordial seas. The scientific community has not taken this possibility lightly. Missions are being designed specifically to investigate Europa's secrets. NASA's Europa Clipper, launching in the coming years, will perform dozens of close flybys of the Moon, mapping its surface in detail and probing its subsurface with radar, magnetometers, and spectrometers. It will search for evidence of the ocean's depth, its chemistry, and the potential plumes that connect it to the surface. Each pass will bring humanity closer to the truth, whether Europa's ocean is simply water and rock or something far more profound. The European Space Agency's JUICE mission will complement this effort, exploring both Europa and Ganymede. Together, these missions mark the beginning of a new era, the age of ocean world exploration. They will test the limits of our engineering and the depths of our curiosity, bringing us data from a place where sunlight fades and the line between habitability and mystery blurs. But before these spacecraft arrive, scientists have already begun decoding Europa's signals from afar. Its magnetic field, induced by Jupiter's immense magnetosphere, fluctuates in ways that strongly suggest a conductive layer beneath the surface, exactly what one would expect from a salty, global ocean. This evidence, combined with thermal modeling and surface chemistry, leaves little doubt. Europa's ocean is real, vast, and dynamic. Yet, the question that lingers above all others is not whether Europa has an ocean, but what that ocean contains. Could primitive life have formed there independently of Earth? If so, that would mean life is not a rare accident, but a natural outcome of chemistry wherever conditions allow. The implications stretch far beyond Jupiter, to Saturn's moon Enceladus, to the icy worlds of Neptune and Pluto, and even to exoplanets orbiting distant stars. Europa challenges us to rethink life itself, to imagine biology not as a fragile flame, dependent on sunlight, but as a tenacious force capable of thriving in the dark, under pressure, in oceans of alien chemistry. It reminds us that the boundaries of the possible are far wider than we once believed. The surface of Europa is both a barrier and a bridge. It protects the ocean from radiation and space, but it also isolates it from direct contact with the cosmos. For billions of years, whatever lies beneath has evolved in solitude. If we one day reach that hidden sea through probes, landers, or drills, the encounter will be unlike anything humanity has ever experienced. We may see strange ice formations, floating mineral rafts, or chemical traces of metabolism. Or we may find nothing, save for sterile water and rock, a reminder that not every ocean gives rise to life. Yet even in that case, Europa's significance does not diminish. It stands as proof that liquid water, the essential ingredient for life, can exist in abundance far from the warmth of the sun. It broadens the map of where life might be found, showing that worlds once dismissed as frozen wastelands may, in fact, be vibrant within. Europa also reveals a deeper truth about our place in the solar system. The same gravitational forces that stir its ocean are tied to Jupiter's immense presence, the same planet that may have shielded Earth from cometary bombardment and influenced the formation of the solar system itself. In this way, Europa's story is intertwined with ours. The same cosmic dynamics that make life possible here have also sculpted distant, icy worlds capable of harboring their own mysteries. As our technology advances, so too does our reach. In the future, robotic explorers may land on Europa's surface, melt their way through the ice, and send submersible probes into the ocean below. Cameras may one day capture images of alien marine landscapes, the dance of minerals in ice in total darkness, or perhaps the faint motion of life itself, simple organisms drifting in alien currents beneath an eternal sheet of ice. For now, Europa remains a promise of discovery, of wonder, of confrontation with the unknown. It is a reminder that even in the coldest corners of the solar system, nature's creativity persists. The same forces that forged volcanoes on Io and magnetic fields on Ganymede have also crafted an ocean world beneath the ice, a world that could change everything we know about biology, chemistry, and the resilience. Europa is silent but not still. Every crack, every ridge, every plume tells a story of movement, of energy, of renewal. It is a living paradox, frozen and flowing, barren and alive, distant yet intimately connected to us. Its surface may be cold, but its heart beats with hidden heat and untold secrets. In our search for life beyond Earth, Europa stands as one of the brightest beacons. It whispers through the darkness, calling to the curiosity that defines our species. Someday soon, we will answer that call. And when we do, what we find beneath the ice may not just reveal Europa's story, it may reveal our own. Chapter 4. Ganymede and Callisto, Giants of the Outer System. Far beyond the molten plains of Io and the hidden seas of Europa, two worlds drift through Jupiter's immense shadow, Ganymede and Callisto. They are the quiet sentinels of the Jovian system, ancient and enormous, shaped by forces that echo from the dawn of the solar system itself. If Io and Europa are worlds of energy and change, then Ganymede and Callisto are monuments to endurance, cosmic archives preserving billions of years of planetary history. Together they are the largest and the most mysterious of Jupiter's moons. They represent two very different paths taken by worlds born from the same cosmic nursery. One, Ganymede, is alive with hidden depth, magnetic, layered, and dynamic. The other, Callisto, is a world frozen in time, an untouched relic of the early solar system. Their differences tell a story of creation, transformation, and survival in the harsh outskirts of Jupiter's gravitational empire. Ganymede first commands attention through sheer scale. It is the largest moon in the solar system, even bigger than Mercury. If it orbited the Sun instead of Jupiter, it might well be classified as a planet in its own right. It possesses a diameter of over 5,200 kilometers, a world of ice and rock, encased in layers that reveal the fingerprints of complex internal activity. Beneath its icy crust lies something astonishing, a metallic core generating a magnetic field, the only moon in the solar system known to have one. That magnetic field was first detected by NASA's Galileo spacecraft in the late 1990s. When the instruments began recording data, scientists were stunned. No other moon, not even Europa, exhibited such behavior. The readings indicated that deep inside Ganymede's interior, molten material, likely an iron-nickel core, was moving, just as it does within Earth. This meant Ganymede was not a frozen ball of ice, but a differentiated, geologically complex body with layers that hinted at a dynamic past. Imagine standing on its surface. Above you, Jupiter would hang enormous in the black sky, its disk filling much of the horizon. Auroras would shimmer faintly where the magnetic field interacts with Jupiter's vast magnetosphere. Around you stretches a terrain unlike any other, a world of contrasts. Bright icy plains glint under distant sunlight, while darker regions of older rock mark ancient surfaces, battered and fractured. Grooves and ridges run for hundreds of kilometers, relics of tectonic movement that once reshaped the moon. Ganymede bears the scars of motion, the signs of a world that once groaned and flexed under forces beyond imagining. Scientists now believe that beneath its crust of ice lies not one ocean, but perhaps multiple layers of water and ice stacked like pages in a cosmic book. Between these layers there could exist salty seas kept liquid by heat rising from the moon's deep interior. If this model is correct, Ganymede's total volume of water may exceed all of Earth's oceans combined several times over. It would be a world rich with the most precious resource in the search for life, liquid water, even if buried far beneath a frozen shell. But Ganymede's story is not one of constant activity. It may once have been far more geologically alive, reshaped by tidal heating and differentiation during its youth. Over time, as its orbit stabilized and the tidal forces diminished, it cooled, and its once molten core slowly began to solidify. What remains is a moon balanced between dynamism and silence, an echo of a more turbulent era. Its surface today is a mosaic of frozen plains and craters, its interior a hidden archive of oceans and metals. The magnetic field that surrounds Ganymede does something else extraordinary. It creates miniature auroras, glowing belts of energy that ripple near the poles. As Jupiter's magnetic field sweeps past, it pushes and pulls Ganymede's auroras, causing them to rock back and forth. By measuring that movement, scientists detected a powerful clue. The rocking pattern implied that beneath the surface, an electrically conductive layer must exist, a salty ocean deep below the ice. This elegant dance between magnetism and water confirmed what had long been suspected. Ganymede, like Europa, may be an ocean world. Its presence challenges the boundary between moon and planet. It possesses a core, a mantle, an ocean, a crust, and an atmosphere, albeit a thin one of oxygen molecules, produced when radiation splits water ice. Ganymede is, in essence, a miniature Earth frozen in the outer solar system, an example of how planetary processes unfold even in distant realms where sunlight is faint and warmth comes from within. Yet while Ganymede hints at hidden vitality, Callisto tells a different story, one of stillness, endurance, and preservation. Callisto orbits even farther from Jupiter, nearly 2 million kilometers away. It is the outermost of the Galilean moons, and unlike its siblings, it has remained geologically quiet for billions of years. Where Ganymede has grooves and ridges, Callisto has craters, countless craters. Its surface is the most heavily cratered in the solar system, a silent record of impacts stretching back to the earliest days of planetary formation. Each crater tells a story of cosmic violence, collisions with asteroids and comets, when the solar system was young and chaotic. Some are vast, spreading for hundreds of kilometers, overlapping like ripples frozen in stone. Unlike Earth, where erosion, tectonics, and atmosphere erase ancient scars, Callisto preserves them all. It is a world that has barely changed in 4 billion years, a fossilized memory of the solar system's youth. And yet, beneath that ancient crust, there may still be mystery. Data from Galileo and later telescopic studies suggest that even Callisto could harbor a subsurface ocean, though colder and deeper than Europa's or Ganymede's. It might be trapped between layers of ice, faintly warmed by the radioactive decay of elements in the moon's core. If such an ocean exists, it would be isolated, sealed away for eons, its chemistry utterly alien. The possibility expands our understanding of habitability. Even worlds that seem frozen and inert could, under the right conditions, hide liquid water and perhaps even the faint possibility of life. But Callisto's true significance lies not only in what it might conceal, but in what it preserves. Its surface serves as a geological time capsule, a map of impacts that reveals the history of the outer solar system. By studying Callisto, scientists glimpse the violent processes that shaped not just the Jovian system, but the planets themselves. It is the control case in a cosmic experiment, a moon that never underwent internal differentiation, that never melted or reformed, that remains as it was, untouched since the solar system's earliest dawn. If we imagine Ganymede as a restless giant, Callisto is the eternal witness, the historian of Jupiter's domain. It speaks not through motion, but through memory. It shows us what the other moons once were, before tidal heating and magnetic energy transformed them. In its craters lie answers about the frequency of impacts, the composition of primordial debris, and the scale of early planetary bombardment. By reading its scars, we read the ancient story of how worlds collide and coalesce. Despite their contrasts, Ganymede and Callisto are bound together by their shared origin. Both formed in the swirling disk of gas and dust around Jupiter, a miniature solar system within the solar system. As Jupiter's immense gravity sculpted this disk, heavier materials settled closer to the planet while lighter ices and volatiles accumulated farther out. That is why Ganymede, nearer to Jupiter, developed a dense, differentiated structure, while Callisto, at the system's edge, remained mixed and primitive. They are two outcomes of the same birth, separated by distance and fate. Today, spacecraft and telescopes continue to study them with renewed fascination. The JUICE mission, Jupiter Icy Moons Explorer, is set to orbit Ganymede, mapping its magnetic environment and probing its deep structure. It will reveal how the moon's magnetosphere interacts with Jupiter's, how its oceans move beneath the ice, and how its surface evolved through eons of bombardment. It will pass near Callisto as well, capturing data from a world that may hold the oldest landscape in the entire solar system. These missions are not just about curiosity. They are about context. Ganymede and Callisto together form the bridge between the inner and outer worlds, between the active and the ancient, between energy and silence. By studying them, we can understand how the solar system distributes heat, chemistry, and water across vast distances. They help explain why some moons became volcanic like EEO, others oceanic like Europa, and others frozen like Callisto. Ganymede also offers a preview of something grander. In its layered interior, scientists see the potential blueprint for super-Earths and exoplanets orbiting other stars, worlds with ice, metal, and magnetic hearts, capable of retaining oceans far from sunlight. It reminds us that planetary complexity is not limited to the inner solar system. Even in the cold, dark outskirts, nature builds worlds of staggering diversity and beauty. Callisto, in contrast, teaches humility. It shows what happens when a world escapes transformation. It stands as a control sample for planetary science, untouched, unchanged, yet invaluable. If we ever establish bases or outposts in the Jovian system, Callisto may even become humanity's stepping stone. Its distance from Jupiter means it is less affected by intense radiation, making it one of the safest locations for future human exploration beyond Mars. In this sense, the silent moon could one day play host to the noisiest of species, us. Both Ganymede and Callisto challenge our imagination in different ways. One suggests that life's ingredients may exist in unexpected places, shielded beneath frozen shells. The other reminds us that not all worlds are meant to change. Some are meant to remember. Together they form a dialogue between past and present, between movement and stillness, between what was and what might be. When we look at them through our telescopes, what we truly see is time itself. Ganymede shows us the middle chapters, the evolution of a moon from chaos to structure, from molten to Callisto shows us the prologue, the untouched origins of everything that came after. They are cosmic bookends to Jupiter's system, containing within their contrasts the story of planetary diversity on a grand scale. Beyond their physical characteristics lies a philosophical resonance. They invite us to reflect on endurance and transformation, the two forces that shape everything, from moons to lives. Ganymede embodies change, the internal heat of motion and evolution. Callisto embodies stillness, the wisdom of survival through time. Both are necessary. Without motion, there is no renewal. Without memory, there is no meaning. In the vast court of Jupiter, these two ancient giants orbit in silence, their faces turned eternally toward the planet that shaped them. Ganymede hums faintly with the music of magnetism, while Callisto sleeps under the slow drizzle of cosmic dust. They have circled their parent for billions of years, watching as comets fell, as sunlight shifted, as the outer solar system grew colder and quieter. And through it all, they have endured. To study them is to study time itself. To visit them will be to walk among the ghosts of creation, one alive, one preserved, both sacred in their own way. They remind us that the universe does not hurry. Its greatest masterpieces unfold over eons, written in ice and rock, magnetism and memory. And as humanity prepares to send its probes, its cameras, and perhaps one day its footsteps to those distant worlds, we will not only be exploring moons, we will be visiting reflections of our own planet's history and destiny, the forces that built Earth, the oceans that gave rise to life, and the ancient silence that still waits, patient, at the edge of Jupiter's realm. Ganymede and Callisto are not just moons. They are time capsules. They are teachers. And they are proof that even in the furthest, coldest corners of space, the story of creation continues, written in frozen oceans, metallic hearts, and the unyielding patience of eternity. Chapter 5. The Future of Jovian Exploration, Unlocking Cosmic Secrets. For more than 4 centuries, Jupiter's moons have captured the human imagination. From Galileo's trembling hand as he first sketched those 4 moving lights to the high-definition images sent back by robotic emissaries, each new generation has drawn closer to understanding them. But the story of Jupiter's moons is not finished. It is only beginning. What lies ahead is a new age of exploration, one defined by precision, endurance, and the determination to uncover the universe's deepest truths. In the decades since the Galileo mission ended, technology has transformed the way humanity explores space. Instruments that once filled entire rooms now fit into the palm of a hand. Sensors can detect single molecules, and computers can sift through data faster than any human mind. These advances have opened the door to missions once thought impossible. Spacecraft that can orbit hostile worlds, survive radiation that would destroy unprotected electronics, and probe through ice to glimpse hidden oceans. At the center of this new age stands Europa Clipper. Designed by NASA and scheduled to embark on its journey soon, it will perform dozens of flybys of Europa, mapping every ridge, every fracture, and every potential plume. Its radar will send pulses through the ice, revealing layers that no eye has ever seen. Its spectrometers will study the composition of salts and organics on the surface, searching for signs that materials from the ocean below have reached the surface. Its magnetometers will measure how Jupiter's field interacts with Europa's own conductive interior, providing the clearest picture yet of the ocean's depth and salinity. Each pass will last only minutes, but every moment will be packed with discovery. The spacecraft will dip through radiation belts fierce enough to destroy unshielded instruments in seconds. It will rely on hardened electronics and an intricate flight path that uses Jupiter's gravity to slingshot around the planet. And when its data reach Earth, scientists will piece together a world that, for all its distance, feels astonishingly familiar. An ocean world orbiting a gas giant, a distant echo of our own Earth-Moon system. Across the Atlantic, the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, pursues a broader vision. Where Europa Clipper focuses on one moon, JUICE seeks to understand the entire Jovian system as an interconnected network. It will study Europa, Callisto, and finally Ganymede, becoming the first spacecraft to orbit another moon besides our own. Its instruments will map surfaces in exquisite detail, test the composition of thin atmospheres, and probe subsurface oceans using magnetism and gravity. Together, these two missions form a partnership that spans continents and generations, a testament to the global nature of curiosity itself. But robotic explorers are only the beginning. The ultimate goal is to touch, to sample, and to know. Engineers are already designing cryobots, robotic probes capable of melting through ice, carrying sensors and mini-submarines into the oceans below. Such a machine could one day descend through Europa's crust, drifting into darkness, scanning for heat, minerals, and perhaps the faint chemical signatures of metabolism. The data it could return would redefine biology, chemistry, and our understanding of what it means for a world to be alive. Long before humans set foot there, our machines will prepare the way. They will learn how to land safely on shifting ice. They will test communications through kilometers of frozen crust. They will map radiation levels and determine where future explorers can survive. The Jovian system is one of the most dangerous environments in space. Jupiter's magnetic field traps charged particles that move at nearly the speed of light. Any unshielded human would receive a lethal dose of radiation in minutes near Europa's orbit. But beyond these deadly belts, at the distance of Ganymede and Callisto, conditions begin to calm. There, on the outer moons, future bases could one day rise, small outposts built for research, power generation, and scientists dream of a Jovian gateway, a human crewed station orbiting Callisto or hovering near Ganymede, powered by nuclear reactors and protected by thick walls of water and ice. From such a foothold, astronauts could control robotic missions in near real time, directing dives into Europa's ocean or exploring Io's volcanic plumes. It would be the first permanent human presence in the outer solar system, a bridge between the inner worlds of sunlight and the dark frontier beyond. Why go so far? Because the answers waiting there reach beyond any single moon. By studying the Jovian system, we learn how planets form, how energy moves through ice and rock, and how life might arise in unexpected places. Jupiter itself, immense and ancient, preserves the early chemistry of the solar system. Its moons show how that chemistry evolves, from molten rock to frozen oceans to worlds that may breathe beneath the ice. Together, they form a living laboratory for understanding not only our origins, but the nature of exoplanets that orbit other stars. Around those distant suns, astronomers are finding Jupiters everywhere, massive gas giants with families of smaller worlds. Some lie in habitable zones, where conditions may mirror those of Europa or Ganymede. Each discovery pushes a simple but revolutionary idea that life's potential may not depend on sunlight or warmth, but on energy and water in any form. In that sense, Jupiter's moons are not just local wonders. They are cosmic templates. To understand them is to understand the galaxy. The coming decades will see even more ambitious missions. Plans are being drawn for sample return missions, in which spacecraft would scoop material from Europa's plumes and deliver it safely back to Earth for analysis. Future probes may orbit Jupiter's polar regions, studying the magnetic environment that drives its auroras and influences its moons. One day, a fleet of autonomous explorers might roam the system, mapping gravitational anomalies, photographing hidden craters, and listening for seismic whispers beneath the ice. Each new generation of data will refine our picture of how worlds evolve. We will learn how tidal heating reshapes moons, how magnetic fields interact with conductive oceans, and how radiation alters chemistry at the surface. Step by step, we are building a model of complexity that reaches far beyond Jupiter, a model that could explain similar processes on Saturn's moons, Neptune's Triton, and even the icy bodies orbiting in the Kuiper Belt. Yet amid the mathematics and engineering lies a deeper reason for exploration, one rooted in wonder. When humanity first sent Voyager past Jupiter, the images changed everything. We saw volcanic eruptions on Io, cracks on Europa, storm systems larger than Earth swirling across Jupiter's face. Those pictures reminded us that the universe is not static. It is alive with motion and transformation. Each mission since has carried the same lesson, that every discovery opens 100 new questions. The future will also bring collaboration beyond Earth itself. Artificial intelligence will assist spacecraft in decision-making, allowing them to adapt autonomously to changing environments. Miniature drones may accompany landers, mapping terrain from the air. Instruments will become lighter, smarter, and more sensitive. Data will stream back to Earth in real time, and virtual reality simulations will allow anyone, scientists, students, or dreamers, to experience these worlds as though standing upon them. Jupiter's moons also serve as moral mirrors. They challenge us to confront our responsibility as explorers. These are pristine environments, untouched for billions of years. The act of visiting them carries the burden of preservation. International space agencies are developing strict planetary protection protocols to ensure we do not contaminate these potential habitats with Earth's microbes. If life exists there, it deserves to be discovered as it is, not as an echo of ourselves. And if we find no life, the value remains immeasurable. Because to look into the darkness and find silence is still to learn what the cosmos allows and what it withholds. Even absence can teach. It can remind us that life on Earth is precious, a fragile phenomenon born of rare alignments of chemistry and time. Jupiter's system, in this sense, becomes a mirror of our own existence. Its diversity, fiery Io, watery Europa, magnetic Ganymede, silent Callisto, reflects the diversity of life's possibilities. The planet's gravitational pull binds them together, just as the sun binds all planets, just as gravity binds galaxies. Everything connected, everything moving, everything part of one grand unfolding. Future generations may one day watch the Jovian system rise in their sky from habitats orbiting Mars or stations drifting in deep space. They will know that long before them, people dared to imagine such things. They will study ancient recordings of the Europa Clipper and JUICE missions, artifacts of a time when humanity first began to reach outward in earnest. And they will continue the story, building, flying, discovering. Perhaps centuries from now, a human or an intelligent probe will descend into Europa's ocean, lights piercing the darkness, revealing landscapes never before seen. A faint glimmer will pass the camera, perhaps mineral, perhaps something that moves with intention. If such a moment comes, it will not belong only to scientists. It will belong to everyone who ever wondered what else might share this universe with us. The future of Jovian exploration is the future of curiosity itself. It is a promise that we will not stop asking questions, that we will continue to seek and to learn even when the answers are uncertain. Each mission is a thread woven into a tapestry stretching from Galileo's lens to the edge of interstellar space. It is a testament to the power of imagination and to the human need to understand. And so, as we stand on the edge of this new era, we look outward to Jupiter, the great guardian of the solar system, the keeper of moons and mysteries, and we look inward to the same drive that has guided every explorer. The next steps will be taken not by one nation or one generation, but by a species that has always looked up and wondered. In the centuries to come, when ships made of alloys yet to be invented sail through Jupiter's shadow, when robotic divers swim beneath Europa's crust, and when human eyes watch the sunrise from Ganymede's horizon, the same truth will endure, that exploration is not only about finding other worlds, but about discovering who we are in the Jovian system will continue to turn, Jupiter spinning, moons orbiting, tides rising and falling under alien skies. And somewhere across the vast gulf of space, the light of human curiosity will follow them, unblinking, determined, eternal. In the end, Jupiter's moons remind us that the universe is still full of mysteries waiting to be found. Beneath layers of ice and storms of fire lie worlds that challenge what we know about life, time, and creation itself. Humanity's journey through the Jovian system is only beginning. A journey not just through space, but into the heart of our own curiosity. As long as we keep reaching, the cosmos will keep answering.